So here we are in Chapter 8 on rotational kinematics. Now you guys remember kinematics. Kinematics is the study of motion in a straight line. So rotational kinematics is the study of motion in a circle. So in this section we're going to learn about rotational motion and angular displacement. The simplest kind of rotation is when you're spinning around a central axis. There's an axis of rotation. So the first thing we're going to look at is the definition of angular displacement. So with linear displacement, we can just measure how far an object traveled in the x direction or the y direction. But with angular displacement, because things just keep turning around and around and around, what we're talking about is the angle that our object turns through in a certain period of time. Now the SI unit for angular displacement is the radian. So what is a radian? I know some of you have had to switch back and forth between radians and degrees in your calculators, but I'm not sure that you actually know what a radian is. So in radian measure, the angle in radians is defined to be the arc length divided by the radius. So the arc length is just the distance, the length of this arc right here. So as I'm sure you all know, the arc length of an entire circle is 2 pi r. It's just the circumference of a circle, just the distance all the way around one time of a circle, of any circle. So the angular displacement in radians is the arc length divided by the radius, and the arc length divided by the radius, 2 pi r divided by r, is just 2 pi. So every circle all the way around once is 360 degrees, but it's also 2 pi radians. Alright, so let's take a look at an example. Here we have two adjacent synchronous satellites. So it's two satellites that are staying directly above their position of the Earth. The satellites are put into an orbit with radius 4.23 times 10 to the 7th. That should be 10 to the 7th, not 107 meters. And the two adjacent satellites have an angular separation of 2 degrees. Let's find the arc length, S, that separates the satellites. Alright, so to solve this problem, first we need to take a look at what we have. Well, we have the radius, and we have the angle in degrees, and we have our equation. And let me write the equation again for you. So the equation says that the angle in radians is equal to the arc length, which is S, divided by the radius, which is R. Now this angle needs to be in radians. So we have it in degrees, so we simply need to convert from 2 degrees into radians. So we multiply that by our conversion factor. And if there are 2 pi radians in 360 degrees, we want to put the 360 degrees on the bottom so that the degrees cancel out. And then our answer is going to be in radians. So 2 times 2 pi divided by 360 gives us an angle of 0.0349. 0.0349 radians. Alright, so now that we have theta, that's the 0.0349, and we have r, we need to do S is equal to r theta. So S is equal to 4.23 times 10 to the 7th meters times 0.0349, and S is equal to 1,476,548 meters. Alright, so now you've learned a little bit about angular displacement, and now we're going to talk about angular velocity. So the average angular velocity is represented by the Greek symbol omega, and it's defined as the angular displacement divided by the time. That sounds familiar. So in linear terms, velocity equals displacement divided by time. And in angular terms, angular velocity is equal to angular displacement divided by time. That seems awfully familiar. Alright, so let's take a look at an example. Here we have a gymnast on a high bar, and the gymnast swings through 2 revolutions in a time of 1.9 seconds. And we're going to find the average angular velocity of the gymnast. So the first thing we have to do is we say, well, I'm going to write the equation again. We have, hang on, angular velocity is equal to angular displacement divided by time. So if the gymnast swings around twice, the angular displacement is 4 pi. And divided by 1.9 seconds is equal to the angular velocity. So angular velocity is equal to divided by 1.9, 6.6 radians per second. Yes, of course, here we are at angular acceleration. So the instantaneous angular acceleration, which is written as alpha, is the angular acceleration at any given instant. And we're going to calculate that by taking the change in angular velocity divided by time. Alright, so let's review a little bit. So with regular kinematics, we measure displacement in meters, and we just use the letter X or Y or Z for displacement. In rotational kinematics, we measure displacement as angular displacement, and we measure it in radians. In kinematics, velocity is displacement divided by time, and we measure that in meters per second. And in rotational kinematics, angular velocity is angular displacement divided by time, and that's measured in radians per second. And in regular kinematics, acceleration is A, and it's just change in velocity over time. And in rotational kinematics, acceleration, angular acceleration, is alpha, and that equals the change in angular velocity divided by time. Alright, we'll practice more on Monday. Have a great weekend.